Hello everyone. So today our project we're going to demonstrate is development of energy efficient high-speed array multiplier using transmission gate logic. We have built the using Cadence Virtuso. If you open a terminal and go to our main library manager, in the first we're going to see our MSL. So because we have built our array multiplier using its complete MSL. This is our schematic view of our MSL, which is very good and full ladder. And this is a symbol of MSL. Logic. So for our comparison, we have fast transistor and CMOS and transmission. This is the schematic of fast transistor for array multiplier. And this is the symbol of our array multiplier. And this is the precedence. And if you open our radial window and choose a measuring parameter, we include that measuring parameter for us. We are going to only done a transmission transient analysis, and now let we choose an output line and input lines. Now let we run. It may take some time. Yeah, now we got. Let we maximize it and flip the waveform now. Yeah, it's done now. Now we go into the browser and we choose the parameter results that we have get for this waveform. And this has our output waveform for a array multiplier in CMOS logic. That's it. Now let we go on to see fast transistor logic. So this is a schematic view of our multiplier and pass transistor, and this is a symbol of a multiplier and pass transistor logic. And now let me see the test bench of a pass transistor. Now let me open our radial window, and same as previous, let me choose our measurement file, and now let me apply it and OK. Now go for transient analysis and click OK. Now choose our output lines and also the input lines. We got our waveforms. Let me split it now. Here the main problem that we are facing here is there is a lot of voltage drop. So here will be see there is not complete 1.8 volt was received at the output. So this shows there is a lot of drawbacks in fast transistor logic. And we're seeing the parameter around three more parameters that is null value was be present, which shows we can't able to find those because of this voltage drop. And now we're going to see our transmission gate logic, and this is our schematic of transmission gate, and this is our symbol of an array multiplier and transmission gate logic. And if we move on to our test bench, as same, we're going to open our ADL window and going to choose our measurement file model library, add it, click apply and OK, and choose a transient analysis. Selecting our output lines and input line. Now run. Now we got our output. Let us split it now. Here we can clearly see our output. There is no voltage drop was been done, and all the parameters will be received correctly, and there is no losses in anywhere. Now let me explain you the transistor count that we required for build our single MSL. First, the MSL was completely built using AND gate and full ladder. For that full ladder, we are using two XOR gate, two AND gate, and one OR gate. For a static CMOS, it takes around 48 transistor to build a single MSL, and for pass sensor, it takes around 28, and in transmission gate, it's 40. So here, while we based on a transistor count, here the pass sensor is very less comparatively. And these are the parameter that we have seen previously in our waveform window. First is a total number of area of transistor that we have used in CMOS is 894, and for pass transistor is around 520, and for transmission gate is around 742. And in worst case delay for CMOS it's around 119.50 picosecond, but in pass sensor we can't able to find out this due to incomplete voltage swing. And in transmission gate is around 110.67 picosecond. So in worst case, we can choose transmission is better. And in static power, CMOS is 82.84 nanovolt and pass is 65.29 nanovolt and transmission is 145.18 nanovolt. So here the pass sensor is better, but as we can't able to find the worst case delay. So it's one of a drawback that we have faced till now. And in dynamic power, CMOS was 5.18 microvolt and power sensor is 3.26 microvolt and transmission is 4.81. So here also when the power sensor was low, but we can't able to find the worst case and rise time on a fall time. So in that view, while we comparing the CMOS pass pass sensor transmission gate logic, here the transmission was been best, and in rise time we can't able to detect the pass transmission get logics, and also in fall and also in power delay we can't able to get the output values. So here in so that's why for the last three parameter we can compare only with CMOS and transmission. So in that the rise time was lower in the CMOS and the fall time was also been lower in CMOS logic, but in power delay the transmission gate is slower. So overall these are the um, Transit count parameter that we have directly taken from our results from Cadence page, a resulting page. And BSM shows the transistor count. At the down, we can see the output parameter that we have measured using our model library by inserting measurement files and parameters for being shown you here in graphical view in percentage for easy understanding. Here the area was been lower in pass, but comparing with the CMOS and transmission, the transmission is lower here. And also in wo- worst case delay also it was lower as compared to CMOS, the transmission is slower. And in static power, here the pass density is lower. While but in comparing with CMOS and transmission, CMOS was much lower. And in dynamic, here the transmission is lower, and coming to rise time, we can't able to find the value for past sensor and lifetime fall time and also in power delay product. So in these last three parameters, uh, the transmission is better in power delay product, and another two rise and fall time, the CMOS is better. Overall, comparing the six parameter, around four parameter shows that transmission gate logic is better, and we can't able to compare it now because of pass sensor. We can't able to get around three plus parameters was been empty, and but finally comparing CMOS and transmission, we go with transmission because of the four parameters shows the transmission is better.